Okay, so it's my absolute pleasure to introduce Benjamin Steinberg. Ben, he'll be talking on the simplicity of Nekrashevych algebras of contracting self-similar groups. I hope I didn't butcher that, probably did.
Well, I don't know how to pronounce his name that well either, so.
So Ben is from the City College of New York, and this is joint work with Nora Sakax from York. Thanks, Ben.
Well, actually, she's in Manchester now. I forgot to update this, so sorry. She's in Manchester. She was in New York when we did this, and then I didn't update this. So are my slides now on the big screen? It's okay? All right. So, yeah, I'm not sure how you guys will slow me down if you have questions, because you guys don't have like chat or something because you're not on the computer. So this is all joint work with Nora. And the algebras we're looking at are ample groupoid algebras. They're étale groupoid algebras. And they are also quite related to Leavitt algebras. Not Leavitt path algebras, but the original Leavitt algebras when your graph is just a bunch of loops. So it's kind of a hybrid combination of kind of two things. So I'm going to begin by explaining what's a self-similar group, because I'm not sure if people know it. And even if you do, I'm going to actually describe it from the group theory point of view. Because before I was doing this kind of ring theory, I was doing group theory, and I did some work on self-similar groups just as groups. And so once you start looking at things a certain way, you tend to keep looking at them that way. All right, so what I need is a finite alphabet with at least two elements. So an alphabet's just a set, but we're going to use this alphabet to form words, so that's why we call it an alphabet. And what we're doing is uninteresting if you have only one word. Okay. So now what I'm going to do is I'm going to take the Cayley graph of the free monoid on X. So unfortunately, star is overused in math, and people use X star for the free monoid, but it has nothing to do with stars and operator algebras. So I apologize. So the Cayley graph is you just have as vertices the elements of your monoid, which in this case are all words over the alphabet X. In this case, my alphabet's just 0 and 1. And then you connect things by an edge if they differ by generator. And so this is what the Cayley graph looks like for a free monoid on two generators. It's a rooted binary tree. If you had n generators, it'd be a rooted n-ary tree. And if you look at the boundary, the infinite paths starting from the root, from the identity, then they're labeled by a unique infinite word, right? So if I go all on the left side, I'll see 0, 0, 0, 0, 0 repeated. If I go this way and then this way and then this way, I'll see like 1, 0, and then a bunch of ones. So infinite paths correspond to infinite rays starting from epsilon, from the empty word. Epsilon is for the empty word. Infinite rays starting at the empty word correspond to x omega, and there's a natural topology on the boundary of a tree, and it's the same as the product topology on x to the omega. And in particular, the automorphism group of this tree therefore acts on its boundary, so it acts on infinite words. And so self-similar groups are certain groups of automorphisms of this tree, and sometimes I view them as acting on finite words or on the tree, and sometimes on infinite words, and I'll go back and forth. So the first thing to notice is if you have an automorphism of this tree, it must fix the root. So if we look at this example, every vertex has degree 3, so it has 3 neighbors, except the root. The root has 2 children, and it has no parent. So the root has degree 2, and all other vertices have degree 3. Since an automorphism of a graph preserves degree, every automorphism must preserve the root. And of course, this would be true for however many generators you have. The root always has one less neighbor than everybody else. And therefore, it has to permute the subtrees hanging from the root. So I call these trees Tx, and they are just the words that begin with the letter X. So for instance, in my previous picture, T0 would be the tree hanging out here because it would consist of all the words starting with 0, and T1 would be the tree here of all the words starting with 1. And then because you can identify these two trees, maybe I'll put the picture back up, I can identify the left tree with the right tree by just deleting the first letter. If I delete the first letter, it looks exactly like the whole tree. And so I can identify the left tree, the right tree, and the whole tree by just deleting the first letter. And if I do that, then if I have a permutation which moves, an automorphism of the tree, which moves, say, x to y, then the way it moves the x tree to the y tree will be given by another automorphism, which is denoted by g restricted to x, which is sometimes called the section. If you want to just write it in algebra, and this is how the analysts usually do it, you would just say that g of xw is g of x, and then you do the section thing to g and have it act on w. And the section thing kind of has a cocycle kind of property. So people in the names of these things keep changing, but nowadays most of the self-similar group people call this a section. And similarly, you can define the section for any word so that the same formula holds, and you can just do it inductively. The section of g at x1 ... xn is you first take the section at x1, take that guy's section at x2, and keep going. Okay, so this is how automorphisms of a tree behave. Let me see, are there any questions before I move on? I'm not sure, maybe someone can convey them to Danny, who can convey them to me. Because I can't really see anyone's face to see if people are following. Between the mask and everybody's small. It's okay?
Yeah, I think there's no questions, man.
Okay, I guess it's better just ask questions at the end. I don't know. If you're really stuck, just stop me. It's just, I'm not sure about the logistics. So a subgroup of the automorphism of a group of a tree, of one of these rooted trees, is called self-similar if it's closed under sections. So if I go back here, I'm going to go back to the picture because this is like geometric group theory. If I have an automorphism, it might move this 0 tree to the 1 tree. And it will do it by some automorphism, but that automorphism of the tree might not belong to my favorite group of tree automorphisms. So the self-similarity property says that whenever I look at how my group element moves one subtree to another, it must always belong to my group G. So that's what this being closed under sections mean. So it means not only is each section a tree automorphism, but it's a tree automorphism which belongs to G. So for instance, the whole group is self-similar, but there are many others. The most famous self-similar group is Grigorchuk's 2 group, which is quite famous because it has bizarre properties, which I'll mention later. And there are also Gupta-Sidki P groups for odd primes. So these are examples of finitely generated infinite groups where every element has order a prime power. In the Grigorchuk 2 group, every element has order of power of 2. And in the Gupta-Sidki P groups, they all have order of power of P. So for a long time, it was even an open question if such infinite finitely generated groups existed. Grigorchuk and Zook, they used a self-similar representation of the lamplighter group to disprove the strong form of a TS conjecture on L2 Betty numbers. So I'm just kind of advertising the area. Bartholdi and Nekrashevych used self-similar groups called iterated monodromy groups to solve Hubbard's twisted rabbit problem in complex dynamics about 2 fractals. And we're going to use throughout that any self-similar subgroup of the automorphism group of a tree acts on infinite words, because the infinite words are the boundary of the tree, and the automorphism group acts on the boundary. Now, the way people in practice build self-similar groups is from automata. And there's some really good lecture notes by Gupta-Sidki from Brasilia in the CIMPA lecture notes and math series on automata groups, or groups generated by automata. The definition I'm going to give of automata is good if you're doing self-similar groups, but the notion of automaton is from computer science, and the definition they give there would look totally different, but it's just basically the same thing. So for us, an automaton is going to just be a finite set of automorphisms of our tree with alphabet X, which is closed under sections. So you can have a finite collection of elements, and any section of any element from the set A is some other element, or maybe the same element of the set A. And they're usually given by pictures, and I'm going to draw the pictures on the next page and explain how they work. What you do is you draw what's called a state diagram or a Moore diagram, or just some people will call that the automaton. You have vertices, which are just the elements of our finite set A, and then you have edges, which are labeled. The left side of a label is one of the letters from my alphabet X, and the right side is, so think of X as the input letter, and A of X is the output. It's where A sends X. And then you move to your section at X, which will be another element of A, because A is closed under sections. I have a picture on the next page, But what's important for us is if you generate a group by an automaton, you always get a self-similar group. And these are called automaton groups, and they were studied first in the early 1970s in the Ukraine, particularly by Alyoshin and others. And one thing that's nice about automaton groups, if you're a group theorist, is that they always have a decidable word problem. So it's a way you can build up very complicated groups that automatically have a decidable word problem. You can use these automata and computer science to solve the word problem. So I'm going to draw an example of an automaton, because if you pick up a paper on automaton groups or self-similar groups, which is not written by an analyst, you'll probably see this kind of picture. I know the people who do self-similar groups in analysis tend to work kind of with the more algebraic formulation. But anyway, it's good to see these. So this is the odometer, or adding machine. A is for adding machine. So let's try to parse this picture. So if I'm at A and my input is 0, that's the left-hand side. My output is 1, so A of 0 is 1, and that's the right-hand side. And I move to the section of A at 0, which is B. If A's input is a 1, it should output a 0, so A of 1 is 0, and my section at A is A. So that's how this picture encodes the sections and the transformation. Similarly, B, if its input is a 0, it outputs a 0, and if the input's a 1, it outputs a 1, and then both sections are B. So you just stay put and you never leave B. So now you can actually compute the input of any word by just looking at this picture. So I'm going to show you how A evaluates on 1, 1, 0, 1. So my input is 1, so I'm supposed to output a 0. And then because this is a loop, I stay at A. And now I repeat, my input is 1, so I should output a 0 and stay at A. Now my input's a 0, I'm supposed to output a 1 and go to B. So I go to B. Now B, my input is 1, I output a 1, and I'm done with my word, so I don't go anywhere. So you can basically compute from this picture what it does to any word by just tracing on the graph. You don't need to use all this, stuff. And so this is a computer science. This is called a finite state machine, or a transducer, or an automaton in computer science. And people have studied these, for ages. What does A actually do? It adds 1 to a two-adic number, least significant digit first. So when I add 1 to this binary expression with 1 being in the ones place, the 1 becomes a 0 and I have to carry. When I add a 1 to the first, so the first digit's a 1. When I add 1 to it, I get a 0 and I carry, which means I have to add 1 again. But if the first digit's a 0, then it's going to change to 1 and I'm never going to do anything again. In fact, B is just the identity. And so this group generated by A and B is just the integers. Okay, so that's how one of these funny things works. Okay, so if you've never seen one of these before, it takes a while to get used to, but this is the easiest way, I think, to work with these automata groups. So here's an automaton which generates the Grigorchuk group. It's a little bit more complicated. It has 1, 2, 3, 4, 5 vertices, so 5 states. These things are called states. E just as the identity. It's exactly like in the last picture. No matter what input it gets, it outputs the same letter and never leaves. So this E is just the identity. A, what does A do? If the first letter is a 1, it changes it to a 0. If the first letter is a 0, it changes it to 1. And then it moves to the identity, so it never does anything again. So A just changes the first letter of a word. B, C, and D are more complicated. You can check that B, C, D, and E generate a Klein 4 group. So if you forget about A and just look at B, C, D, E, they generate a Klein 4 group. E is the identity. B, C, and D, what they do is they look for the first, they fix the word that's all ones, because if I have the all one word, I just go around this circle and these guys don't ever change 1. But if I have a word which starts with 0, it will either change the first letter after the 0 to a 1 if it ended up here, or it will change the first letter, or it won't change anything if it ends up here. And so what happens is, this depends basically on where the first 0 occurs, mod 3, because this guy's going in a cycle of length 3. So what happens is if you have a word which is not all ones, then 2 of these 4 guys will fix it, 2 of these Klein 4 group guys will fix it, and the other 2 will change the first letter after the 0 to the opposite letter. And from that description, you can check that they really give a Klein 4 group. But when you throw an A, suddenly you get something complicated. You get a group which is finitely generated. It's just infinite. Just infinite means it's infinite, but all of its proper quotients are finite. So it is not. It's just barely infinite. It's a 2 group, meaning all its elements have finite order or power of 2, and it has intermediate growth, which means that balls in the Cayley graph grow faster than any polynomial function, but slower than any exponential function. And it was the first example of such a group. It was also the first example of a group which is amenable. Any group of sub-exponential growth is amenable, but it's not built from amenable groups by doing the obvious operations which preserve amenability. So it's not what's called elementarily amenable, or elementary amenable. Okay, and in all the work by Grigorchuk and Gupta and Sidki, who followed Grigorchuk with simpler, or not simpler, but with different examples for odd primes, they all exploited their groups have a property which is called contracting. So I'm first going to define it the way that Grigorchuk did, and then I'll give you the modern Nekrashevych definition. So kind of the original theory was developed in the Ukraine, and then Grigorchuk and Sidki and others further explored it. And then kind of an abstract theory was made by Nekrashevych, who kind of did it from a more theoretical point of view and tried to kind of figure out a general theory as opposed to, you know, understanding lots of interesting examples. Okay, so roughly speaking, an automaton group is contracting if there's some constant less than 1, a positive constant less than 1. I guess it's probably usually not going to be 0. I guess it could be, can't really be less. It can't really be 0. It should be positive. With the property that the word length, so L is the word length. The word length is the smallest size of a reduced word that maps to your element of G. And the contraction condition says that the word length of each section is at most lambda, which is less than 1, times the word length of your word for all group elements of sufficiently large word length. So what that means is that if you have a big word, all its sections are smaller. And so that's what you use for induction. So when Grigorchuk proves this as a torsion group, he shows that all small words have finite order. And then he uses this contraction property to say inductively the sections have finite order or order of power of 2. And then he deduces the whole thing does. Now, if we keep iterating taking sections, we're going to keep decreasing things by lambda to a bigger and bigger power. And since lambda is less than 1, we're going to get smaller and smaller words. And so that's the idea of this. And then Nekrashevych did this in a way that makes sense for self-similar groups, even if they're not finitely generated. So here's the Nekrashevych definition of a contracting group, which is what I need for this talk. So a contracting group, so a self-similar group is contracting if there's some finite automaton n, so that given any element of your group, when you take its section at words of length k or bigger, you end up in n. So there, even though the group has many sections, for any given word, all sufficiently large, for any given group element, all sufficiently large sections belong to this finite set n. Okay, so it's a little bit hard to digest, but if there is such an n, there's a smallest one, and it's called the nucleus. So I'll give an example in a second, or explain how it's related to the other contracting property, which is in a sense where the examples come from. So again, being contracting means that given any element of your group, so being contracting means there's some finite set n of elements, which is closed under sections. That's what it means to be an automaton. And any element of your group has all its sections from some point on in the set n. So there's sort of a limited amount of sections you can see from elements of your group if you go far enough down. And there is an algorithm which, given an automaton, tells you whether it's a nucleus. And if you have an automaton which generates a contracting group, it will produce the nucleus for you. You can do it on GAP or any computer software which has automaton groups. However, it's not known if you can decide if an automaton is contracting. So if your automaton is not contracting, it will never produce the nucleus. In the classical approach, with word length, if you, the sections contract by a factor of lambda for all words sufficiently large. So therefore, basically the nucleus is going to be those guys which do not have their sections contracting by lambda. there's only finitely many of those, and anybody else, their sections will eventually be, by iteratively taking them, they contract by lambda to bigger powers, and so eventually they get small enough that they don't contract. Anyway, so examples of contracting groups are the Grigorchuk group, the Gupta-Sidki groups. There are things called GGS, which are Grigorchuk-Gupta-Sidki groups, which somehow generalize the previous guys. There are Unit groups, which I'm going to define later. And there are other fancy groups, Basilica groups, Hanoi Tower groups. Let me maybe back up for a second. The adding machine is contracting. The nucleus of the adding machine is A, the identity, and A inverse. So you can check that bigger and bigger powers of A, their word lengths go down. So A's word length doesn't go down because A sections are A and B, but powers of A, roughly, their word lengths go down by a half. And so they do contract. The Grigorchuk group is contracting, and this guy is the nucleus. So this is the nucleus of the Grigorchuk group. It's generated by its nucleus. Many of the most interesting self-similar groups are generated by their nucleus, but it doesn't have to be. Okay, so that's the nucleus. Okay, so that's the end of my introduction to self-similar groups. I realize this is fast if you've never seen one before. But, and since I only have 40 minutes, I can't really go into that many examples of them. Let me tell you about the algebras. So Nekrashevych introduced C-star algebras associated to self-similar groups, which generalized Kuhn's C-star algebras. And then he later considered the analogs with coefficients in the field. And the C-star algebra is, of course, a completion of the complex Nekrashevych algebra. And the algebraic thing is like a Leavitt algebra, which I guess Leah's been talking about. And there are a number of people who studied these Nekrashevych algebras over fields, including Clark, Exel, Pardo, Sims, Starlings, me and Nora. The C-star algebras have been studied by even more people. I think Rusba has also studied these as well. So I'm going to give, you guys already know what a Leavitt algebra is, but I'm going to give a sort of non-standard introduction to them. So if we have our alphabet X, then if we take a vector space with basis the infinite words over X, we can get an operator which just puts X on the front of a word. I call this push X because an infinite word you can think of as a big stack, and then this puts X on the top of a stack, and computer scientists call this pushing onto a stack. Believe it or not, Leavitt algebras are rediscovered by computer scientists. Everybody keeps rediscovering the Kuhn-Krieger relation. And then there's sort of the adjoint operator, which a computer scientist would call pop X. What does it do? If you have a word which begins with X, you remove the X from the beginning. And if the word begins with a letter which is different from X, then you can't really pop X from the beginning, so you just say 0, because 0 is kind of garbage. And then there are some obvious relations. There's this relation. If I push an X on the top of the stack, the only letter I can pop, then if I remove X, I didn't do anything. And if I try to remove anybody else, well, then I'm trying to remove the wrong letter, so I'm going to get garbage. And then there's the Kuhn-Krieger relation, or the Kuhn's relation, which says that the sum XX star is 1. And that's because whatever the first letter of W is, the X star will pop that and then push it back on. So you didn't do anything. And so the algebra defined by these relations is known as the Leavitt algebra that was introduced by Bill Leavitt in the 50s and then sort of rediscovered by Kuhn in the operator theory setting, rediscovered by computer scientists interested in stacks. And it's a finitely presented simple K-algebra which acts faithfully on this vector space. Now, if I have a self-similar group over Tx, then it acts by x omega on permutations. And so I can build a permutation representation or a permutation module or a quasi-regular representation. People have all sorts of names for this. By just basically extending the action of G on x omega linearly. And so the natural thing to do is we have two things which are represented on this vector space, the self-similar group G and the Leavitt algebra. So let's look at the algebra generated by those. It's going to obviously have the Leavitt relations and the multiplication table of G, but there are some additional relations coming from the self-similarity. For instance, if I put an X on the front of an infinite word and then do G, well, that's going to be the same as G of X followed by the section of G. Because once I put X at the beginning, you're going to do G of X to that X. and then you're going to do gx to your original word. And there's a dual thing for the stars, which is slightly more complicated to think about. And so the Nekrashevych algebra is the K-algebra generated by G and these x and x stars subject to the Leavitt algebra relations, the multiplication table of G, and relations 1 and 2. So you just formally define it by generators and relations by adding 1 and 2 to the multiplication table of G and the Leavitt algebra. And then it turns out that the K-algebra generated by the Leavitt algebra and G acting on this vector space is the unique simple quotient of the Nekrashevych algebra. There's something kind of analogous in the operator setting that Nekrashevych proved, but it's kind of slightly different, but it's basically the same flavor. Maybe it's exactly the same, but I don't understand operator algebras well enough to know if it's exactly the same. But anyway, it smells very similar. The proof looks different, of course. So the simplicity of the Nekrashevych algebra is basically the same thing as saying that this natural representation on infinite words is faithful, because that's the unique simple quotient. And of course, the complex algebra must be simple in order for the C-star algebra to be simple. That's not difficult to show. And Nekrashevych C-star algebras are étale groupoid C-star algebras for an ample groupoid. I've been told they've been defined ample groupoids. And Nekrashevych algebras are the algebras, sometimes called Steinberg algebras, of the same groupoid. And these groupoids are always effective and always minimal. So they satisfy the two properties that for Hausdorff groupoids give simplicity. But these groupoids associated to Nekrashevych algebras are almost never Hausdorff. They sometimes are. Almost never is a bit of a strong word, but often they're not. And therefore they're good for trying to understand the question of when is an algebra, a groupoid algebra for a non-Hausdorff groupoid simple. So let me just give some background. In 2015, in his paper, Nekrashevych showed that the algebra of the Grigorchuk group is not simple in characteristic 2. Remember, the Grigorchuk group acts over the alphabet 0, 1, and it had this Klein 4 group, B, C, D, and E, which I told you fixes the all one word, and any other infinite word is exactly 2 elements agree on it. 2 of them will fix it, and the other 2 will switch the first letter appearing after 0. So in characteristic 2, this guy will either be 4, if you act on the all ones word, it will be 4 times the all one word, which is 0 in characteristic 2, or it will be 2 times your original word plus 2 times the word where you flip the first thing after a 0, and that's still going to be 0 in characteristic 2. So this guy is in the kernel of that action. And well, you have to check this, but it's true. This guy is not a consequence of the Kuhn-Krieger relation. This is a non-zero element of the Nekrashevych algebra, but in that representation, it's killed. So it's not simple. Clark, Exel, Pardo, Sims, and Starling showed in 2018 that the Nekrashevych algebra of the Grigorchuk group is simple over all fields of characteristic different than 2. Actually, in their paper, they just say characteristic 0, but their proof works over any characteristic other than 2. So this was the first example that I'm aware of a groupoid algebra, which is simple over some fields and not others. For Hausdorff groupoids, it's simple over every field or none. So this was the first example where the characteristic of the field matters. And actually, it's a result of me and Nora that it's only the characteristic that matters. The actual field doesn't matter. You can always replace the field by the prime field or an algebraic closure. It doesn't matter. It's only the characteristic that matters. The authors above also showed the Nekrashevych C-star algebra of the Grigorchuk group is simple. Nekrashevych, in an unpublished thing that he sent to the authors of the above paper, showed that the algebra of the Grigorchuk-Erschler group is simple over no fields. This was the first example of a groupoid which was minimal, effective, non-Hausdorff, whose algebra was not simple over any field, and also his C-star algebra is not simple. The Grigorchuk-Erschler group is a kind of variant of the Grigorchuk group, which was introduced by Grigorchuk and studied by Erschler, who computed its exact degree of growth. So there are examples where weird stuff happens. And all these examples, Grigorchuk group and Grigorchuk-Erschler, are contracting. Nekrashevych showed in his original paper that C-star algebras of contracting groups are finitely presented. They're universal C-star algebras given by a finite set of generators and relations. And the same happens for Nekrashevych algebras over fields. It's generated by the X and X stars and the nucleus. And then the relations are just the Leavitt relations and those relations of the Nekrashevych algebra involving nucleus elements. You can show that all the other relations come from those. And since the nucleus is finite, that's a finite presentation. This also shows the algebra depends only on the nucleus and not on G. So you can assume that, that G is generated by the nucleus. So now I'm going to sort of state our main theorems. And then some applications. I won't have time to explain any proofs, which is good. So our first theorem is if you have a contracting group over an alphabet X, then either the Nekrashevych algebra is not simple for any field, or it's simple for all fields but finitely many positive characteristics. So it can't be non-simple for infinitely many positive characteristics. And if it's simple in any positive characteristic, it's simple over C. We also showed that there's group theorists like algorithmic problems. We showed there's an algorithm which, given the nucleus of your automaton group, of your contracting group, outputs all the characteristics for which the algebra is not simple. So either it will tell you that, yes, it's simple over every field, or it will say, no, it's not simple in characteristic 7, 11, and whatever your other favorite prime number, 101, whatever. So it will so there's a way to determine it. And of course, there's some theoretical description of simplicity that underlies the algorithm. So that, you know, if you're given your favorite family of self-similar group, contracting groups, you can probably figure out whether it's simple or not. And so we did that. We looked at many well-known families of contracting groups, and we used our, you know, what our algorithm basically tells you to do. But of course, you can't run an algorithm on infinitely many groups, but we use the theory behind it to figure out what's happening. We also do a construction. We show that for any finite set P of primes, there is a contracting group whose Nekrashevych algebra is simple precisely over the fields whose characteristics don't belong to P. So remember, I said in number 1 that there can be only finitely many bad characteristics unless it's simple over no field. And what this third thing is saying is that there's no restriction on the set of bad characteristics. For any finite set of primes, we can build a self-similar group so that that set of primes is exactly the set of bad characteristics. And if we do it by a construction, we give a very explicit construction of the group. So to give an example, I'm going to look at something called Sunik groups. These were invented by Zoran Sunik to be the close cousins, or siblings even he calls them sometimes, of the Grigorchuk group. These are the self-similar groups that behave most like the Grigorchuk group. And I'm going to tell you how to construct it in a very abstract ring theoretic way. So you take a prime P, and you take a polynomial over Z mod P. This is Z mod P, not the p-adics, of degree n, whose constant term is non-zero. So you start off with a polynomial like 1 plus x squared. Then we take the companion matrix, so everybody knows from undergraduate linear algebra, hopefully, or from graduate linear algebra, what the companion matrix of a polynomial is. The fact that f of 0 is not 0 means the companion matrix is invertible, right? The companion matrix has characteristic polynomial f. So this is exactly the condition that this is invertible. Now we build a self-similar group, GPF, whose alphabet is going to be Z mod P, and it's generated by the cyclic permutation of the P trees hanging from the root. So in other words, sigma adds 1 to the first letter, and then treats the rest of the word by itself. And there's also a copy of Z mod P to the n, which acts in a way which imitates the way the Klein-Ford group, which is Z2 cross Z2, acts in the Grigorchuk group. So you're probably not going to be able to absorb it, but roughly speaking, the way Z mod P to the n works is it fixes the first letter of every word. It's sectioned at 0, so V is going to be a vector in Z mod P to the n. And its section at 0 is you just multiply by this companion matrix. That's another element of Z mod P to the n. Its section at the last letter, P minus 1, is do this permutation raised to the last entry of V. And all its other sections are the identity map. Okay, anyway, this is somehow a generalization of the Grigorchuk group. I don't expect you to absorb this in real time, but it's known to be a contracting group, and its nucleus is Z mod P to the n and the powers of sigma. So again, sigma is just a permutation which adds 1 to the first letter of a word and then leaves the rest of the word alone. So for instance, the Grigorchuk group is you take your prime to be 2, and you take your polynomial to be this 1 plus x squared, which I normally associate with the Fibonacci sequence. And the companion matrix of that is the matrix you associate kind of with the Fibonacci sequence. And if you do that construction, you get that Grigorchuk group. The Grigorchuk-Erschler group is the polynomial x squared plus 1 over z mod 2. There's another famous group, the Fabrikowski-Gupta group, which is 3 and x minus 1. Anyway, it's not so important. And let me just tell you what are the, and Sinek gave necessary and sufficient conditions for this to be a P group of intermediate growth. So I'm probably going to end by just telling you what our theorem says for these guys, because this includes the Grigorchuk group, the Grigorchuk-Erschler group, and many other famous groups. So if I have a Sinek group, it's given by a prime P and a polynomial with non-zero constant term over z mod P. If it has degree n, then the Nekrashevych algebra is going to always be simple for every field when the polynomial is linear, when it's degree 1. If n is greater than 1, so it's a polynomial of degree at least 2, then this companion matrix is an invertible matrix. So it acts on the lines in zp to the n. This is a vector space of dimension n. We can take its projective space, which is just the lines. And this guy acts on the lines. And if the action is transitive, then the Nekrashevych algebra will be simple over all fields except those of characteristic P. This is what happens for the Grigorchuk group. The Grigorchuk group acts transitively on all the non-zero vectors. In Z2 cross Z2, there are 3 non-zero vectors, 1, 0, 0, 1, and 1, 1. And the companion matrix of 1 plus x squared just acts like a cyclic permutation on those guys. So we get this condition. And if n is greater than 1 and this guy does not act transitively on the lines, then this is not simple. The Nekrashevych algebra is not simple over any field. And that's what happens for the Grigorchuk-Erschler group. And when this guy does act transitively, then it follows from Sinek's result that this is a P group of intermediate growth. So all the guys in situation 2 are P groups of intermediate growth, which have simple Nekrashevych algebras over every field except those of characteristic P. They also have a simple C-star algebra. Somebody kind of extended our results to the C-star direction. A Japanese guy whose name I'm not remembering. The Grigorchuk-Erschler group is x squared plus 1. The companion matrix for x squared plus 1 is the permutation matrix 0, 1, 1, 0. It's the permutation matrix which switches the 2 coordinates. And the permutation matrix which switches the 2 coordinates fixes 1, 1. So it fixes this line. And therefore, it doesn't act transitively on projective space. And that's why this thing is not simple. Okay, and I think I'll stop there because I'm supposed to be stopping now, right? It's 40 minutes, right?
Yeah, I guess that's fine, Ben. Thank you.
So, obrigado.
Any questions for Ben? No questions? Okay, in that case, let's thank Ben again. Thank you very much, Ben.
Thank you guys for coming. Sorry I couldn't be there in person.
Next time.
Next time. I hope you guys are enjoying good weather, at least, unlike us.
Yes. All right, thanks.
Okay, thank you. Guess I should unshare my